Okay, so we'll start with that 5-minute video. It's perfect because I need to run something to the office and probably get yelled at for a minute because like I didn't do it the right way. But forgiveness. Okay, so anyway, when the video ends, TA, you're in charge if I'm not back. Okay, when it ends, you guys have a nice discussion about van der Waals forces, or you could study your matching terms or vocabulary. So this is just a review, not really a review, I guess. We're going into London dispersion forces, which were weird. We said it happens when one atom or molecule moves close to another one. It induces a temporary dipole, so there is an attraction and yada, yada, yada. This will hopefully help explain it a little bit more clearly. And here we go. Don't worry, I'll slow it down instead of 2 times. Okay, here we go. I don't know out there if you'll hear the audio. If not, I apologize.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 16. It's on London dispersion forces, which were first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here. But before we move on and talk about it, think about the forces in this picture. Which are greater, the forces within the individual people holding their atoms together, or the forces between them holding them together in this photo? Well, clearly it's the forces within your body. And so this is the first video in a set of videos that talk about bonding between molecules and within molecules. And so if we think of them all as molecules and we move them apart a little bit, there are going to be the intermolecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive forces. These are intermolecular between molecules. And they're going to be found in all atoms and molecules. So everything is attracted through London dispersion forces. It's really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also, as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase? It's going to be these London dispersion forces. So right here, I have 2 helium atoms. And so they're going to have 2 protons on the inside, 2 electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are 2 what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those 2. It's fairly simple. It's going to hold them together. Now it's just instantaneous. It's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres. And as a result, these ones are going to have more surface area, more contact area. So we're going to have greater forces. And so the boiling point of N-pentane is going to be higher than that of neopentane based on these London dispersion forces. What else? The polarizability. And polarizability, remember, is the squashiness. The more electrons we have, the more forces we're going to have. And so this right here is a protein. Proteins are massive in size, And a lot of that three-dimensional shape comes from these London dispersion forces. Also, it's going to explain why, as we go down in the periodic table, let's look at the halogens right here. Halogens are going to have the same valence electrons, but as we go to fluorine, chlorine, bromine, and iodine, we're actually going to go from gases, fluorine, chlorine, to liquid bromine, and then solid iodine. And that's all going to be based on these London dispersion forces. As the atoms get bigger, they have more electrons. We're going to have more of this uneven electron. And then finally, pi bonding. That's going to have orbitals that overlap. It forms something called a pi bond. If we increase the number of pi bonds inside those molecules, we're going to increase these London dispersion forces. So again, what are they? They're attractive in nature, found in everything. It's uneven electrons create these temporary dipoles. Remember, what increases it, our list would be contact area or surface contact. Also, the polarizability, which is going to be based on the molecule size, and pi bonding. Can you do that? Could you explain these trends? If you can remember those three things, you've got it, and I hope that was helpful.
There you go. Why was
And
that
so
what?
they're going to have two protons on the inside.
Okay, so they're kind of weird that they even exist, but hopefully, I don't know, where did he have that drawing? There's a temporary attraction
Two
between the
electrons on
negatives
the
and the
outside.
positives.
And so as we move them,
Right there. So they're always moving. Electrons, they'll be on one side randomly all of a sudden. Then there'll be an attraction between the electrons and the nucleus of the other substance, and a repulsion. So they will create a temporary attractive force right here. And if there's like trillions and trillions of these things happening, then that ends up being something that is significant that we do care about. And that's why nonpolar substances do have the ability to be liquids and solids. When they're cold, it doesn't have to be super cold, but the cooler, the more this would matter for sure. And that's why, like, all the nonpolar things that we generally talk about are gases at room temperature. So, yeah, good. Are we kind of all right with what a London dispersion force is? Okay. What are the ways we have large London dispersion forces? It increases with contact area. Okay, so long straight molecules have higher van der Waals forces. You okay with that? Or London dispersion forces? Sorry, they're the same thing. All right, so we got to know what that means. If it's longer, and you're ruining my calculator. Oh, hello. Oh, thank you. Oh, I'm an error. So if it has more intermolecular forces, then what do we know about its melting and boiling point? It's higher. So if you were given on a test a picture and it said which one has the higher melting and boiling point, you would choose the one that was typically longer and straighter than just a blob, right? So we have neopentane. This is sometimes called cyclopentane versus N-pentane, which is just when it's straight. Okay, all of those, the shape will definitely affect its physical properties because of London dispersion forces. All right, polarizability. This is really, really tested on the AP test. This is the term they usually will be asking you. The larger the molecule, the more polarizable. And when I say larger, I mean the more electrons it has. So the more electrons it has, the more polarizable it is, and typically the greater IMF, which means that substances, and he talked about it, we have fluorine as a gas, low melting and boiling point. Iodine's a solid, high melting and boiling point, right? And that's because iodine is a large molecule with 53 electrons, which are more polarizable than just 9 in fluorine. Are we okay with that? Okay. So contact area, polarizability. And what else did he talk about? Molecule size is just, it's part of the polarizability. Wasn't there one more? Oh yeah, pi bonding. This one we're not really stressed about. It's usually not assessed in AP, but where do pi bonds come from? All right, overlapping, and they exist in, starts with the D, ends with able. Double or triple or quadruple, which we don't really talk about. We don't get pi bonding until we have multiple bonds, right? So it's not really tested, but typically if you had an ane, which is all straight, versus an ene, wait, I shouldn't say straight, they're all singles, or an ene where we have a double, the ene would most likely have a higher melting and boiling point because it has pi bonding, which increases the van der Waals forces or London dispersion. I keep saying them. Van der Waals forces is like what we call all of these. They're also called intermolecular forces, but they're van der Waals. That's the overall umbrella. Then they have the 4 ones. So if I say van der Waals are increasing, it's the same as saying London dispersion are increasing. Okay, good. Chart. Where'd the chart go? Okay, I don't know. You have any questions about it? It's something that if you really want and you need to know better, you should read about. Or watch Bozeman again. Or there's 15 minutes from Khan Academy about it. But either way, okay. So back to the notes. So far we've had ion dipole, dipole dipole, London dispersion forces. In red right here, London dispersion forces are found in all atoms and molecules. So if you are ever given a list and it says what type of intermolecular forces are in this substance, you always should say LDF. They're in every single thing that has electrons. Well, I guess it would be in plasma, but we don't deal much with that. If it has electrons, it is polarizable. It has London dispersion forces. Okay, in general, dispersion forces is generally tend to increase with increasing molar mass. Draw an illustration of a molecule experiencing LDS. Do you want to draw it? Why don't you try? So draw like 2 blobs and demonstrate what they would look like, their electrons and their protons. I didn't realize you were going to do that whole roll. You're like hero status 12 now.
Yeah. Was I not supposed to?
No, it's great.
Okay, good.
I love that you did it.
Okay, good. Are those like good sizes?
They're perfect.
Okay, good.
You're amazing. Let me get you the other thing I can't stand doing. All right. Hopefully, yep. Hopefully this wasn't too hard. If it was AP, I know they give you a little more details. It's say, draw the London dispersion forces diagram for something with 5 electrons or something like that. You okay with that? So you'd put like a +5. Right? And then you'd have like all 5 on one side and all 5 on the other. Now, is that ever going to really happen? No, but it illustrates that temporarily there's an attraction to here and a repulsion as well. Go ahead.
The reason these happen when they're colder is because the electrons move around less, and so the atoms.
It's not really the electrons. Electrons really don't slow down in temperature measurably. It's because these two are closer to each other for a longer period of time. If they're just flying by, even if it did offend the electrons, doesn't matter because it's already gone. So we got to be pretty cold. But like, I don't know, what super cold to me means like close to absolute zero, but we're not going to get that cold. But I don't know. We feel okay with this so far? Not terrible, hopefully. All right, Keely. Oh, I have one last type of intermolecular force, and that is hydrogen bonding. Hydrogen bonding happens in water. We're really, really familiar with that, but it can happen in other things. But you need to be careful. Hydrogen bonding doesn't happen in everything that has hydrogen, though. It happens in a select few things. Okay, so hydrogen bonding is a very strong form of dipole-dipole bonding. That's why at the start I said it's really 3.5, because hydrogen bonding is really just dipole-dipole bonding. Hydrogen bonding exists only between hydrogen and atoms bonded to F, O, and N. Hydrogen bonding accounts for the unique properties of water. All right, in red, these require, N, O, and F. What that means is it has to be bonded to a hydrogen, one of those 3 things. So in water, we know it has hydrogen bonding, and that's because the hydrogen in one is bonded to an O, and the hydrogen in the other is bonded to an O. So there would be hydrogen bonding here. But there would not be hydrogen bonding in this picture. So we would not have OH. Now, without another water molecule, there's not hydrogen bonding. This is just a polar covalent bond so far. And then I put in methane. All right, and I have the H here. Or I could have the H here. Right here, right here, right here. You with me? There is no hydrogen bonding between these. It has to have an H bonded to a very electronegative atom, and that has to be attracted to an atom that has another H attracted to an electronegative atom. So since there's no real dipole created in CH4, this doesn't happen. So in order to see hydrogen bonding, you have to have H connected to an N, an O, or an F. We all right with that? One of the AP videos, let me fast forward it and find it. And it's a really good question. And it's kind of hard to draw, and he already has it. So give me a second. Read this like italices while I look. Hello, Tim. Oh. Now, if you think, why isn't he saying hi to Devin and Nathan? That's because I already did. And I mean, I don't want to go too far. I'm not going to show the video. I'm just going to cut this thing real fast. Oh, that's not what I wanted. All right. Mhm. All right, what we have here, please stick with me. We have bonds 1, 2, 3, 4, and 5. And there's lines and dashes, and it's asking the line or dash that it's pointing at, is that considered hydrogen bonding? So you try it on your own and write down your 4 or 5 answers. And we're looking for yes or no, and then check with your partner, and then we'll go over it together. All right, check with your partners. Seth's hydrogen bonding right now.
We're connecting our mental power so that we can focus.
Well, he's being a genius is what he's doing.
No, you're not the one to be part of it.
There. Now we're on.
I feel so much smarter
You
now.
feel so smart.
Yes.
Yeah, but you might not feel that much smart.
Yep.
You feel their brain power.
So
Why the different colors?
I don't know, just for fun.
Not dark purple, light purple. Oh my gosh.
It's too late.
Looks good.
It's too late.
Looks good. Never mind.
Okay, it looks good. Never
Don't
mind.
even worry about it.
Okay, here we go. Are we ready? So, bond number 1 right here. Is that hydrogen bonding? No, that is a what? That's a covalent or polar covalent bond specifically. All right, or an intra. Good. Okay, how about bond number 2? Is that is a yes. It meets our qualification. We have H connected to O, and we need a F, an O, or an N, right? And it's attracted to this N, which is connected to H. So there's a lone pair of electrons. That's really what we're looking for, is if it's attracted to a lone pair of electrons and it's on an electronegative atom in the first place. Okay, number 3. It is not. How come? All right, so there's no real, there's no dipole here for this to be attracted to. You with me? Since it's sharing the electrons equally. Okay, number 4, what do we got? We got a yes on number 4. It's tricky, but we have this double bond, so it's all right. This one is a maybe, but I'm going to say a yes. All right, we have the O, we got a double bond, which is throwing off the pairs because these would really be right here and right here, right? So I don't know, that's kind of weak. But number 5, what do we say there? This one's a tricky one also. It's a no.
Oh.
All right.
The mental power doesn't work without words.
Okay, these are tricky, but what's missing here in number 5? There's no dipole right here, so it's tricky. Typically though, it's really clear, especially this number 4. That one won't be on the AP because that one's just a little bit too tricky. All right, this piece right here. To determine what type of IMF is dominant, check the type of bonds involved. If there is an ionic bond and a polar substance, the IMF will be ion dipole, like the dominant one. It will have others. If they are both polar, it will be dipole-dipole. It's everything. Well, sorry, salt water is everything. Water would be 3. Yep. All right, and if there are only nonpolar substance, it has to just be dispersion forces. You with me? Okay, so we have some questions here. These come from the test. They're different, but they're extremely similar. These are dashes, not negative signs. Okay, so let's look at all 3 of these. We want to explain why. So all of these are true statements, but we want to explain why. The boiling point of water, ammonia, and methane are 10, -33, and -164 Celsius. Sorry, 100. I don't know where 10 came from. 100. Okay, so we got 100, -33, and -164. Okay, so how do we account for these? We need to think, all right, it's talking boiling point, so it must be asking really about the intermolecular forces. Okay, so what I'm going to do, I'm going to draw, and you don't have to draw on your test, we're just trying to learn it. So we got water, I'm going to draw 2 of each thing. Negative is a temperature. So if it's cold, if it boils at a -164, that means it has really low IMFs. Like they're not attractive at all. All right. So in water, you would have to explain that it has the highest because of what? All right, it has dipole-dipole. And what else does it have? Hydrogen bonding and LDF. Okay, so what else did I have here? I have ammonia, which is NH3. You with me on that so far? This is supposed to be a wedge and a dash. It didn't. I've done better for sure. Okay. In ammonia, what do I have? Is ammonia polar? Yes, it is. You would know the structure for sure says it's polar, right? And then N and H, that's going to be a polar bond. So there's dipole-dipole. Oh, well, crap. There's also hydrogen bonding and LDFs. So now I'm going to drop the class, right? All right, and then methane is CH4. Uh-oh. Okay. Right there. Okay, I'm going to put an attraction right here, some dashes. You okay with that? Okay, in methane, is it polar? No. So are there dipole? No. Is there hydrogen bonding? No. So there's only London dispersion forces. All right, no, that's a good question. Seth asked, what about ionic dipole? Is there anything ionic in these three things? No, so none of them have ion dipole. So this is easy, why this is the lowest. That's an easy answer. Methane has the lowest boiling point because it only has London dispersion forces, and methane is a very small molecule. So the London dispersion forces themselves would be weak. Okay, so it only has weak LDFs. And methane is definitely a gas. It's natural gas. It's what comes out in our Bunsen burners that we light on fire. It was what heated your water for your shower. It's a gas. Okay, so the real hard part of this question is these look like they're the same substance, but their boiling points are pretty far off, right? So why is water so much, does it take so much more energy to boil? Okay, very good. Oxygen is very electronegative. So the H2O, I would say polar covalent bond is significantly more polar. Which means ... greater dipole forces. And it also means stronger hydrogen bonding. Because the electrons are closer to oxygen in water than they would be to nitrogen in methane, or not methane, ammonia. So ammonia would have both less strong dipole. Hello. Yes. Yes. Thank you all. I haven't covered any, but I love milk duds. Thank you.
And we're doing student treats next, so you guys keep waiting.
Barely though. Just kidding. Thank you.
I thought they were going to give you the whole part.
Oh, I'm not that cool. They saved that for Bert. Okay. Are you okay with answering this question thoroughly? It will be slightly different, but it's this exact question will be on the exam. Okay. I feel okay about that. I would not like that answer. It's not detailed enough. Okay. There's a word missing here, huh? It should be at 26 degrees Celsius and 1 ATM. So that's basically ATM, or not ATM, STP, standard temperature and pressure. Chlorine is a gas. bromine is a liquid, and iodine is a solid, which that was covered today. So try and think through your very best way you would answer that. You don't have to write it down yet if you have no faith, but go ahead and write it down if you do have faith. Sorry, faith in yourself. Not- Which one was that, Bill? Oh, Corbin. Yeah, this is not faith in a supreme being, it's faith in you.
Oh my God.
Yeah, that's true. Maybe he is the supreme being.
Don't you hate when you miss a page, Dave? I was on all the vocabulary. I missed this page.
Uh-oh, I hate when that happens. Yep.
I actually did work too. This is what happens when I try. I get it. Yes.
I'm proud of you. I'm way proud of you. Okay, are we ready? Are we ready? Okay. The only type of intermolecular forces between all three of these things is what? Huh? All right, LDFs, right? So this is a question that's assessing your knowledge about how LDFs change. So chlorine is a gas, which means it has the what? Smallest. LDF, mediumest, and largest LDF. You with me? Now that's not the answer. That's like a 1 out of 5 if you just tell me that, because I already know that this is a gas, this is a liquid, and this is a solid. So what I need to know is why chlorine has the smallest LDF. Because it does. Amen.
That's at least 2 out of 5.
Still 1 out of 5. Davis.
Because chlorine has the least amount of electrons, iodine has the most, and bromine is
In the middleest. Okay, that's really close. I'd give him 4 out of 5. I'm looking for one word. No. What? Polarizability. So you should say what Davis said. Say chlorine has the least electrons, which makes it the least polarizable. Iodine has the most electrons, which makes it the most, and bromine's in the middle. So you were super close there. You just needed the word polarizable. Yeah, we went from a 1 out of 5 to a 4 out of 5. It's okay. You're still awesome. All right. We good? That makes sense? All right, we're looking for polarizability. Good. All right, the third question here. Propane, and it gives you C3H8, is a gas, and ethanol, C2H5OH, is a liquid at room temperature. Well, that seems messed up, but it's true. So why? What's the difference? And don't say because ethanol has higher intermolecular forces. That's a 1. Why does it have higher intermolecular forces? And it's because of, any ideas? It has hydrogen bonding between it. Okay. I'm not going to draw the whole thing. Right. So if I draw this out, I'm not going to draw everything. So it's weird in organic chemistry. You just put an R and then a dash. R means representing this. Okay. And don't worry about that. And then I'd have O and H. And if I had another R and it was bonded to an O and it was bonded to an H, what would happen between these two things? Hydrogen bonding. Okay. Now, If this has hydrogen bonding, it also means it has what? Dipole-dipole, because hydrogen bonding is a strong type of dipole-dipole. So the best answer possible, you should say propane only has London dispersion forces. It is a medium-sized molecule. It's not tiny, it's actually not big either, but it has only like fairly weak London dispersion forces. Then you would say ethanol has London dispersion forces and dipole-dipole interactions and hydrogen bonding. And that would increase its melting and boiling point significantly if you now have those three things. Who's with me? Could you answer these on an exam? Could you answer them all the same so I don't have, just kidding. I don't do that on word answers. It's just math. Okay, I'm gonna change slides. You ready? It's more questions here. Will you reason through this with your lab partner? All right. Have you answered this question yet?
You're so immature.
All right, I'm gonna go for it. This one, there's one that's kind of right and one that's way right, in my opinion. In liquids, the attractive intermolecular forces, anyone think it's A? Anyone think it's B?
I thought it was B. I actually
Okay.
didn't think it was B this time, dude.
Does anyone think it's not,
I just
or
don't
C, D,
know.
D? Okay, so the answer is B.
Yay.
Actually, oh, I
Alyssa, I'm so
Okay.
proud of
I'm
you.
proud
I
of
actually
you.
was not just thinking of you.
I'm
I
proud of
actually
you.
knew.
Okay, A, not strong enough to keep molecules from moving past each other. That is true, but there's more details because they still can hold them relatively close, but they can't keep them from holding still. So B is definitely the righter of the choices. What is, oh, sorry, go ahead.
Then that would be like pretty much a solid at that point, right?
On A,
No, for the like.
if it held them close together and was strong enough to keep them, then yes. All right, letter E is just what she says. Strong enough to keep molecules confined to vibrating about their fixed lattice points. That's the definition of a solid. Strong enough to hold molecules relatively close together. Not enough information. Are we okay with that? Very weak compared with kinetic energies of the molecules. That's not useful information. So it was either A or B, and B gave you the more specific correct answer. All right. Here we go. Describe the intermolecular forces for each of the following molecules. So, anyone know what this is called right here? It's okay. You're not required to know this language. If you have one C, it starts with meth. It's methanol. If you have an OH, it makes it an alcohol. So this is methanol. Look real quick. Methane is CH4. Meth really means it's a single C and then whatever comes later. So methanol is, you got your 3 C's and then you have your all functional group, which is OH or an alcohol. Okay, NH3, know what it's called? Ammonia. H2S,
Tim is wondering what the chemical formula of meth is.
methamphetamine. Tim, it's a really complicated thing, but it does have a CH3 group, and that's called a methyl group. Whoops, there's an H there. A methyl group. So methamphetamine, you'd have CH3, and then you'd have the amphetamine, which I won't try and spell because I don't know. I can only make it. I can't spell it. Okay, just kidding. What was this called? Hydrogen sulfide is not technically correct. Dihydrogen sulfide. Now listen. No, if there's more than one of the first, you have to use a prefix. No one in real life calls it dihydrogen sulfide. They just call it hydrogen sulfide. And this is what smells. You know how natural gas stinks? It doesn't actually. It has no smell, but they want you to know if there's like a leak in your house. So they put a little bit of this in and it smells bad. Okay, and then this would be called, we just said it, methane. Okay, so will you think about these things? They're separate. I'm not mixing them together. I'm just saying, what's the intermolecular forces in a bunch of methanol? Okay, take a minute and work through that. Ooh, are we out of here in 2 minutes? Oh boy.
Oh.
All right. None of these have ion dipole. They're pretty, like in this chapter, they're pretty rare. Because we studied ionic solutions in chapter 3 and 4. But still be aware they do exist. All right, I'm going to go pretty quick because I'm down to a minute and a half. So what do we have here? Is there hydrogen bonding? Yes. Is there dipole-dipole? Yes. Anything else? All right, London dispersion forces on all of them, right? Okay, NH3, what do I have? Hydrogen bonding. Dipole-dipole. LDF. H2S, what do I have? All right, is that it? Okay, we'd have to check on the polarity. I think it is polar. If you didn't put it, it's okay. There was this comma was not supposed to be there, sorry. So dipole and just LDF, right? CH4 is LDF only. Not awful, right? Yeah. So I would check this, like I have to. It might be just LDF. All right, adios, online kids. Great to have you. I hope you're all well.